Hi, and welcome back to the second session of the ViViMaT workshop. The second talk today will be held by Jean-François Molinari, the director of the Computational Solid Mechanics Laboratory at EPFL Switzerland. He holds an appointment in the Civil Engineering Institute, which he directed from 2013 to 2017, and a joint appointment in the Materials Science Institute. He started his tenure at EPFL in 2007 and was promoted to full professor in 2012. He's an elected member of the Research Council of the Swiss National Science Foundation in Division 2, that's Mathematics and Natural and Engineering Sciences. Jean-François graduated from Caltech, USA in 2001 with a Master of Science and a PhD in Aeronautics. He held professorships in several countries, including positions at the Johns Hopkins University in Baltimore, at the École Normale Supérieure Cachan, as well as the École Polytechnique de Paris. He received an ERC Starting Grant Award in 2009. The work conducted by Jean-François and his collaborators takes place at the frontier between traditional disciplines and covers several length scales from atomistic to macroscopic scales. Over the years, he and his group have been developing novel multiscale approaches for a seamless coupling across scales. The activities of the laboratory span the domains of damage mechanics, of materials and structures, nano and microstructural mechanical properties, and tribology. Over to you.
So I want to thank Stefan for this wonderful initiative and for inviting me to participate in this event. So in the next 12 slides, I'll be talking to you about elastic interactions between microcontacts. And before I begin, I want to acknowledge my collaborators and past collaborators, in particular Ramin Agababae, who was a postdoc at EPFL in my lab and now faculty in Denmark, and Tobias Brink, also a postdoc previously and now at Max Planck. And currently, son Thamba is finishing his about within a year to finish his PhD at EPFL. So elastic interactions between microcontacts, in particular in relations to adhesive wear mechanisms. And in the title, we have microcontacts, and I want to remind us of what is a microcontact. So we are all aware that surfaces are rough, and because they are rough, we make contacts only at the summits, at the peaks, at the asperities. And here you have a beautiful experimental data from Dieterich and Kilgore from this seminal paper in 1994, where they're shining a monochromatic light in a transparent material. They can get direct imaging of where contact occurs. And this is what is seen here on the right image with different colors for different loads. And as you can see, the real contact area is much, much smaller than the nominal contact area. And this explain a long-standing puzzle starting from Da Vinci and then Amonton and Coulomb that the friction coefficient mu is independent of the apparent contact area. And this is in fact explained by the fact that surfaces are rough. And when you increase the load on the surface, you will increase in proportion the real contact area. And assuming that all the asperities carry resistance to sliding, which here I call sigma j, then we can show that there's a linear dependence between the tangential force and a normal load n, and first the independence of mu, this friction coefficient, on the nominal contact area. So clearly, microcontacts matter to predict the friction. We need to get an understanding of how this map of microcontacts evolve with time and as a function of load. And in the next slide, I want to highlight that in this process of developing microcontacts, asperity interactions matters and mechanics matters. So a nice illustrative way to see this, extracted on those papers in the early 2000s, is to compare what you get if you take a pure geometric model with no mechanics. On the right here, called the overlap or cutoff model. And this overlap or cutoff model is just basically saying that if you have a rough surface like here, and you have this dashed horizontal line, you consider all the asperities to be above the dashed line to be in contact, and those underneath to be not in contact. So it's pure geometry, no mechanics. So if you apply the scheme to a rough surface, a generic rough surface that you can generate on a computer or take from experimental data, and here we're looking down on the interface plane, it's a square plane, we see that we get a contact in this blue patch, which has a complex geometry, but it's kind of bulky. If we take the same surface, but really account for elasticity, that's what you have on the left, or elastoplastic interactions here in the middle, you see that when you push an asperities, well, there's communication with long-range elastic forces, point forces on the surface have a long-range effect. They decay as 1 over the distance to the point source. And as you can tell, as you can see, well, the contact is less bulky and you have appearance of asperities much further away, because as you push on one place, it brings down the neighboring asperities and may bring into contact earlier things that are further away. So elasticity matters. There are interactions between asperities. So now I want to put this context in a perspective of adhesive wear mechanism. So I will not have time to discuss in great details this paper that we obtained in my lab in 2016, but we discussed in this paper a transition in adhesive wear mechanisms at a critical length scale D star that you have here, which is really a function of material properties. And this junction is, this critical length scale tells us that if you have microcontacts of size D that are smaller than D star, well, you will have a plastic flow. So here you have an example in a very simplistic geometry of 2 colliding asperities. One is in red, one is in blue. And as you share the system, those are molecular dynamic simulations, you see that there's a plastic flow of the asperities till you basically close all the gap. And here you can see this in a tangential force profile as a function of time. It's originally quite low, but then it's increasing because we have a more and more intimate contact between the top block and the bottom block. So first, a large tangential force. So this is for junctions that are smaller than D star. And for junctions that are above this critical length scale, again, function of material properties, then something completely different occurs and you start forming a debris. You start to see cracks. They're kind of tiny here on this image. My apologies for this. But now the debris has been created and then it starts rolling and accumulating mass. And the tangential force, in fact, in this case, is very low because it's kind of a roller bearing at the interface and lubricates, in a way, the interface. Okay, so this is a specific microcontact here, leading, for this case, of strong adhesion between those 2 colliding bodies to the formation of a debris. Now, this is an isolated microcontact, but reality is not like this. As I've shown you, we have developed complex contact maps with microcontacts. And here you have an example of this, in which on this plane of contact, I'm showing in red contact that based on a scheme we decide that should lead to a debris, and in yellow those are too small compared to D star and they will not form a debris. So we can count where debris should form at this interface. But the problem is that really they're not that isolated, those microcontacts. This interface is quite populated because we're pushing at already quite a large load. And in fact, if we further increase the applied pressure, we're going to increase the contact area more or less in proportion. So this is a plot of the real contact area A as a function of the normal load W, and we have more or less a straight line. And indeed, as I move here, if I keep pushing, you populate more and more the contact area till percolation, in fact. And clearly, there must be interactions between those microcontacts. It's not possible to think as those microcontacts as isolated. They communicate with neighboring asperities, and one has to wonder what happens in terms of a predictive ability to predict where we form debris and how big they are with our D star parameter. So I'm going to discuss in the next few slides this a paper from 2018 where we use those interactions to potentially explain the transition from mild to severe wear. So the idea is as follows, and that's a very simple schematic taken from this paper, where it's known experimentally that we have different wear regimes. So this axis is a wear volume, and we want to illustrate this here as a function of the applied load, and again, a schematic. So there are different regimes where when the applied load is low, we have very limited wear, And at some point, we'll enter what is called a mild wear regime, where the wear volume is proportional, linearly proportional to the applied load. That's known as Archer wear load, for instance. And eventually, at a critical load, you transition to very severe wear. And usually, in a tribology community, this is discussed as the fact that when you increase the load, you have then suddenly a critical pressure, which might nucleate cracks at defects or grain boundaries in the material. But the problem is that the real contact area is more or less proportional to normal load. So the average pressure is independent of the load. So that's, to me, that's not a completely convincing story. And what might happen, though, is that when we increase the load, we populate more and more the contact interface, and things may start to interact in intricate ways. So this is illustrated on the right. We have on the top row here different images showing that the that the contact is really a multi-scale problem. At a very large scale, things look flat, but if we zoom at the interface, we see that we have asperities, and in fact, we have multiple asperities that contact. And we may zoom on a single asperity here, making a single contact. So perhaps what could trigger this mild to severe wear transition is a transition where we form a single debris at an asperity, to which one where we form a much larger debris, which englobes several asperities. You see you have some gaps here in this debris being formed. And those gaps and this much larger debris may be due to the fact that we have interactions between, and they communicate, elastic interactions between those microcontacts. So that's what we explored with atomistic simulations. So here you have a system. Let's look at this inset image here. We have a system in which now we have not only one junction being made between two colliding asperities, but you have two junctions. Okay, and those are defined by the junction size d and a space in between here that we call lambda. And those junctions here are quite far apart. And you can see this because as you load the system into shear, the stress that develops along a line within the atomistic domain at different amounts of load. So here you start with this blue line, and as you increase the load, you start to develop peaks where you have stress concentrations at the junction between the asperity and the bulk. And you see that those stress profiles do not interact. We have two separated peaks in red here, corresponding to two microcontacts. And thereby, you're going to form two asperities, two debris, my apologies, two debris that will start rolling. And both are proportional, the size of which is proportional to the junction size d. And in red, you see here which atoms within the original configuration end up in those two formed debris. Okay, so it's a region which is fairly limited in space, close to the locations of the junctions. However, if you start to bring those junctions much closer, so you reduce the space in between lambda, and now you see that you develop a peak, a single peak in a stress profile in a bulk, and we have clear interactions between those two junctions, and you end up forming a single debris with little gaps here in between because we have englobed those two different junctions into a single debris. And you see again in red the part of the atoms that in the original configuration would end up in this final debris. So we have interactions. Those were 2D simulations. We can conduct the same thing still with molecular dynamics, but in 3 dimensions with an idea of a dislocation network. Let me skip this, but again, we have two peaks if they are far apart, the junctions, and a single peak if you bring them closer to one another. And the mechanism that is at play here, leading to a single debris, is what we call a crack shielding mechanism. So this can be really, in fact, quantified with a stress intensity factor. But so briefly, we see here this stress profile in a colors red. You imagine this as a high stress, and at all those corners or sharp features in the geometry, here you start to develop high stresses because of applied shear, and at those high stress locations, you're going to nucleate cracks. And we have two outer cracks, one here and the second one here, and two inner cracks that will develop, one here and one will develop shortly here. But the problem here for the inner cracks is that the outer cracks develop faster and they propagate faster, and thereby, my apologies for this, thereby this outer crack is unloading the inner crack, which is closing. So the inner cracks do not succeed to develop, and the outer crack wins in this case. And you see that we are in a process here of forming a single large debris. So this is what we see on this map. We are looking as a function of a space lambda in between the asperities of size D. We look at the volume of a total mass of debris formed, V normalized by V naught, which is a volume formed if you have a single debris at a single junctions form. So when the debris are far apart, here on the side, lambda is large, V over V naught is 2. You are at a line of 2 because we form 2 debris of mass V naught. And when lambda becomes smaller than 1, suddenly the debris mass is shooting. And that's what we call here in this map, severe wear. And so the idea is that as you increase the load, you populate more and more the interface. And as you populate more and more the interface, you are more likely to find parts that will form larger debris that englobe large apparent contact area. So this idea, we've pushed it further recently, but with continuum models that open a lot more possibilities in atomistic simulations because we can probe the space of material parameters in a more efficient way. So here you have an example of phase field modeling with an attainment calculations with Sylvain Collet and Stella Brache. You can see the similar type of mechanisms. If we bring 2 junctions close together, you see that the inner cracks do not succeed to propagate. They stop here. The color here, red, means a high tensile stress, and it stopped. The inner cracks are stopped in their growth, whereas the outer cracks keep growing. And we can do this also with a boundary element method. And with boundary element method in this paper, at the reference at the bottom, we've played with, in fact, not 2 junctions, but many junctions, 3 here in this example, and more within a line, and all the junctions of size D. We can play with the spacing in between, and in some cases, you form a number of separate debris proportional to the number of junctions you have. So it's this case here. And in other cases, we're going to form a single debris with whose volume englobes the apparent contact area, which I call dA. dA is really spanning the whole length over which I have microcontacts. So I know that this plot is too small here on the right, but we can relate with analytical estimates dA on the vertical axis to this the real contact area, dr, which is really made at the places where we have the contact. It's the top of those blue, heavy shaded, sorry, it's not blue, it's red, those heavy shaded red lines. That's a real contact area. So here it's 3 times D, and the apparent contact area takes a space in between also into account. And as you see, we have different regimes. Regimes where we do not form any debris, so it's plastic flow. Regimes where we form separated debris at each individual junctions, and a regime where we form combined very large debris and severe wear. And we can really have analytical estimates of those different regions in those plots that actually match predictions that we also conducted with numerical simulations where we actually follow the crack path. And I will not be discussing this today, but we can do interesting things in 3D with design and optimizations of microcontact places and geometries to form debris of given shapes. So with this, I will conclude my presentation. So I've mentioned in this talk that the important role of a critical junction size to transition to forming debris at a critical size that depends on material parameters. I've mentioned that there are elastic interactions and crack shielding between nearby asperities that change the definition of this critical length scale and help refine a notion of what is an asperity, because an asperity is not a simple object. It may be composed of multiple disjunct microcontacts that are nearby. there is an important distinction between, in my mind, between friction and wear. For friction, the real contact area determines the frictional response, but for wear, in fact, because of communication between asperities, sometimes you may form a collective debris from a collective area, an apparent area, so which is larger than a real contact area. And the microcontact interactions increase with increasing pressure, and this simple mechanistic idea may provide an explanation for the mild to severe wear transition. With this, thank you for your attention, and we'll welcome your questions.
Thanks for your cool presentation, Jean-François. I think I need to cite your papers even more often. And by now, you all know to please leave your questions in the comment section below the video so we can have them answered in the live session on the 3rd of December. See you at the next talk.